All right, let's continue with this handout. Okay, so I was on number 14. You have to rewrite that as a single log. This is this is a sum, right? So it's not a single log. If you want to write it as a single log, then it has to be log base a. I'm assuming it's going to be base a of something. Okay, that's a single log. It's not a sum. So how do we do that? Well, we're going to use a property of logs and we want to put them together. But before we do that, we have to rewrite 1. 1 plus log base a of x is the same as what? How do you write 1 in log base a? Well, you have to know your formula, right? So 1 is the same as the log base a of a, right? The log base a of a is 1 plus log base a of x. And now you have a sum of 2 logs. You can put these two together. That's a log base a of ax. Done. That's it. I wrote it as a single log. Alright? Next one. Okay. I gotta do the same thing. I have to write it as a single log. Therefore, I'm gonna have to change b. I'm gonna have to turn b in log base a. Sorry. Let me explain that quickly here. If you, I'm going to erase that. If you think of the graph of a log base a, I'm going to take a above 1, okay? The graph goes like that, right? It goes like that. This is a point 1, 0, and there's another point right here. If y is 1, then the x is a, right? This is a1. That's why the log base a right here. That's why the log base a of a was 1, right? Okay, anyway. What's the range of this graph? Well, the range of this graph is all real number, okay? For any point right here on this x, you can always find an x that corresponds with it, right? Here's an x, here's a y, and here's the x. For this y, where's the x? Right here. Right? For this y, where's the x? Right here. So there's always a point that will correspond with it. And even if you go fetch it very high, you're going to have to go very far. But anyway, the range, how do we say that? The range is all real number. And if it's all real number, that means any real number can be written, any real number right here, okay, you can write as a log base a of something. Alright? So this is what we do right here. Okay, let's go over it. So let me pause that. Okay, so where was I? All right, yeah. So you got to turn b. I've explained why you can write any number in any log, right, that you want. So how can you write b in log base a? Well, it's based on this property, right? Log base a of a to the anything, okay, is equal to that anything, right? Log base a of a to the x is x. Log base a of a to the square is a square. I mean, so it's based on that. And so b, right? This is gonna be b now. b is just the log base a of a to the power of b, right? Plus log base, there's too many O's here, this is log base a of x, and now you can put them together, right? And then erase that. Okay, so properties of log, sum of 2 logs is the log of a product. So this is a log base a of a to the b times x. That's it, written as a single log. Done. Okay, so now let's solve some equations. This is actually more interesting and more involved techniques involving logs and exponential. So how can we solve an equation with logs right here on both sides, and you got another one right there and another one? Well, there's different approaches to solving equation. This is what I suggest. We've done the same with exponential. You remember, if you have an equality of 2 exponential with the same base, of course, okay, if 2 exponentials are equal, that's 2 output of an exponential function, right? If 2 output of an exponential functions are equal, then the input must also be equal. And the reason for that is that an exponential function is what we call a one-to-one function, right? Output couldn't be equal if inputs were not equal, only because it's a one-to-one function. Well, we can use this property also for log. You know, a log is the inverse function of an exponential. Therefore, a log is also one-to-one. And so if you have, I'm going to use base A, if you have an equality of output of two logs, right here, if two logs are equal, then the input must also be equal. Okay? Oh, that's different. The input must also be equal. Alright, so that's what we're going to use. Again, there are different methods to approach this kind of problems. Let's try this one. Okay, so I need an equality of logs. On the right side, I don't have a log, but hey, we just did some problem where we wrote everything as a single log, right? So let's rewrite the right side as a single log. So you have ln of x squared minus 1 equals, so what's the base right here? The base is e, right? So 5 is the same as ln of e to the 5th power, right? Plus ln 3. Now let's put these two together. So on the left I still have ln of x squared minus 1 equals ln of, so this is a sum of log, that's a log of a product, 3e5. And now, what I just said before is you can just drop the log. Now, please, don't think you're dividing by log. That would make no sense at all. Log is a function. You're not dividing by a function, right? No, you're just dropping the log because the log is a one-to-one function. Okay? So that means that x squared minus 1 equals 3e5. And you know how to solve this equation for x. This is very simple. X squared equals 1 plus 3e5, which means x equals, careful when you remove a square, right? Plus or minus 1 plus 3e5. Okay? And that's the answer. And in this case, I don't need to check if it's true or not. It will work. You may not have understood what I just said right now, but it's something we're gonna have to do actually, okay? Okay, let's solve this one. So what do we do right here? Well, let's put the left side together. This is ln of what? 3x plus 4 divided by 2x plus 1, right? Equals 5. So here, let's rewrite that with a log, right? 5 is the same as ln of e5. And so now you can just drop the log. So you have 3x plus 4 over 2x plus 1 equals e5. How do we solve that? Well, we've done this kind of work before. Let me tell you where. I've given you a function before like that. Let's call it 3x plus 4 over 2x plus 1. And I ask you to find its inverse, right? So the first thing you did was you switch f of x to y, 3x plus 4 over 2x plus 1. Then you switch the x and y, okay? So you call that x equals 3y plus 4 over 2y plus 1. And then right here, you try to solve for y, right? So, and I stressed it at that point. I said, this is now a technique you have to master. You have to remember. Here we go again. This is the same thing there. Look, here's your x, here's your x. You want to solve for x. It was the same thing there. 2y's, and you wanted to solve for y. It doesn't matter here if you have x, e to the 5th, or pi, or whatever. Okay, it's the same technique. All right, so let's see. Let me recall you how to do that. Let me remind you how to do that, rather. Ooh, everything went. Let me remind you how to do that. Okay, so what you want to do right here is multiply by 2x plus 1, right? So you got 3x plus 4 equals e5 times 2x plus 1. Okay, got to solve some x. There's some x's here and some x's there, so I need to have them on the same side. The second thing I'm going to do is distribute my e to the 5th, right? So I have 3x plus 4 equals 2e to the 5th times x plus e to the 5th. Okay, gotta move my x on the same side, right? There's one right here, one right there, so this is what I'm gonna do. I'm gonna move that here, and the 4, I'm gonna move it there. So I have 3x minus 2e5x, okay, equals e5 minus 4. Almost there. This is a step that students most often forget. How do you solve that for x? Well, you gotta have only one x, right? So you factor x. You factor x. So it's 3 minus 2e5 times x equals e5 minus 4. And now you are basically done, right? So x equals e5 minus 4 divided by 3 minus 2e5. Okay, at this point I've solved for x. I'm not sure I have a solution of my original equation at this point, okay? And I will talk about that in class. We have to verify if x is extraneous. Okay, I will go over that in class. So right now, if I have a solution, it will be this one, but I may not have any solution. Okay, if I have one, it's gonna have to be that, but maybe it doesn't have any solution. We'll go over that in class. Okay, let's go over this one right here. I mean, you know, I've solved the equation before, so this one right here, I'm gonna move my ln2 first. I'm gonna write that as ln of 4x plus 1 plus ln of x minus 2 equals ln of 13. Why? Because now you put them together, right? That's ln of 4x plus 1 times x minus 2 equals ln of 13. So this is what? This is, oh, well, how about we drop the ln, okay? Equality of two ln's, you can drop it, and at the same time I'm going to expand. This is 4x squared, minus 8 plus 1 is minus 7x, minus 8 plus 1, yeah, minus 2 equals 13. So 4x squared minus 7x minus 15 equals 0. I hope it factors nicely. Yeah, that's the last one. Okay, just quickly. Let me see. 2x. Come on. Factor, please. 2x. 5 and 3. So I have I have a 6 and a 10. I'm never gonna get. So let's try with 4. 4x. Maybe let's put the 3 right here. 12 and yeah, this is a 5 and a 12. You can make a negative 7. So I want negative 7, so I need a negative 12. Negative 12 plus 5, right? Plus 5x minus 12x negative 7. Yep, that works. So I have x equals negative 5/4 or x equals 3. Now, if I look at the original equation, I gotta check for extraneous roots. And actually here, in this case, we're gonna do it like that by hand this time. There is one. This one, I'm going to discard. Why? Because, look at that. In the original equation, you have the term ln of x minus 2, right? In the original equation. Now, if x is equal to negative 5/4, then that's ln of negative 5/4 minus 2. This is negative, so the whole thing is undefined. This does not exist, okay? This would be undefined. And so it doesn't make sense, so we have to discard the solution. You can never have something negative inside ln. You remember the domain of ln is all real number. 3 is not the problem. 3 is not the problem there. Therefore, the solution is x equals 3, and we discard this one, okay? All right, I'll stop it here.